Here we go, chapter 15. We know we were in 15.1 and we talked about vector fields. And we're going to do some work in a vector field. We're going to look at some problems in a vector field. But when I move to 15.2, we step away from vector fields for a minute. And, well, just for a minute, partially. And we look at what we call these line integrals. And there's two types, and the first type has nothing to do with the vector field. So check this out. It's called a line integral, and it's going to be an integral of a function, f of x, y, a function of two variables, and we integrate with respect to s. We integrate with respect to s, and what is s? It is the, perhaps you recall, it's the arc length parameter. So we integrate with respect to s, which is the arc length of a curve, and we're integrating over a curve. We call this a line integral because we're integrating over some curve c. The curve c does not have to be a line. It could be a line, and I'm still going to refer to it as a curve, or it could be a curve, and then I'll refer to it as a curve. Either way, maybe I should call these curve integrals, but we don't. We call them line integrals. But it's a new thing. We're integrating, now by the way, look at this. This is a 3D function. We're integrating some 3D function over a curve with respect to s, which is the length of that curve. So this is interesting, and it takes a little work. We should actually do a problem. Let's just say then that I have this function, x squared plus y squared. I'm not trying to get too complicated. Let's say, though, that I'm integrating along this curve, and I describe this curve to you. The curve is this semicircle from 2 to -2. Or, yeah, when you do integrate along a curve, the orientation of the curve is important. Are you integrating this way or this way? So we're integrating this function over this curve in the xy plane. And I call this curve a semicircle of radius 2, apparently. So there's a lot going on here at first. But one of the things that's interesting is what we do is we have to, and this is big theme here come for the next few days here, the rest of chapter 15 here for us, is we have to parameterize this curve in terms of the parameter t. So maybe you recall how to parameterize a circle or a semicircle in terms of t. I mean, I need to describe this curve. I mean, a good old rectangular equation is x squared plus y squared equals 4. Actually, that's the entire circle of radius 2. If I want the semicircle, maybe I would solve for y and call it the square root of 4 minus x squared. That would be the upper semicircle. Okay, so this is me talking in rectangular coordinates. I don't want to do that. It's going to be hard for me to get that ds in rectangular coordinates. So I want this parameterized in terms of t. So for a circle, I mean, this makes me, that's why this chapter 15 is kind of cumulative in nature. I mean, here we are at the last chapter of this course, Calculus 3, and it makes me recall quite a bit of things I learned in Calculus 3, and maybe even at the end of Calculus 2, where I learned how to parameterize these curves. A circle of radius 2 oriented counterclockwise like this, I think should be this. X is 2 cos t, and y is 2 sine t. That's the parameterization. Oh, and please tell me how much t I need to finish this semicircle. You know, if it was a full circle, you'd say 0 to 2 pi. It's not a full circle, it's half a circle. I think I need t to go from, t is the angle, I think I need t to go from 0 to pi. So this parameterization of this curve. See, what we do is when we do this integral, I'm going to set this integral up and I'm going to change the whole thing into t's. I mean, as it sits right now, this function I'm trying to integrate is this x squared plus y squared, but I'm going to turn it into t's. Here I go. So the function is x squared plus y squared, but when I turn it into t's, x is 2 cos t, so it's 2 cos t squared. Y is, that's y squared, is 2 sine t squared. I'm still going to need this ds here, but this is kind of messy here. I mean, I've got, my variable is turned into t's, and I'm integrating with respect to s. I got to explain that. Let me do one more thing though. If I am working in t's, I'm going to change this to t somehow. If I am working in t's, then what are the bounds for t? Well, you're integrating this function along this curve. And what are the bounds for t along this curve? 0 to pi. All right, so I'm partially set up here. I got more to explain, I'm sorry. Listen, I got to explain this ds. And so I have to go back to somewhere in the early parts of Cal 3. We learned a little bit about the arc length. I think that was chapter 12. We learned about the arc length s. And the arc length was an integral from a to b. This s is arc length. This is a reference back to chapter 12. S is the integral, the arc length s is the integral from a to b of, oh boy, the magnitude of r prime of t dt. Wow. Okay, so this was back when we were studying vector-valued functions, which were very similar to parameterizations. I mean, this is a parameterization of a curve. X equals 2 cos t, y equals 2 sine t. There's a picture of the curve. The vector-valued function for that curve is simply the x component is 2 cos t, and the y component is 2 sine t. So when we talk parameterizations, I can deal with what's called parametric equations, or I can deal with what's called vector-valued functions. Basically, it's the same thing, but there's no vectors here, and these are vectors. Let me help you here. Let's see. I need what I need for this one. Then, well, hang on just a second. I'm sorry. So what I need for these problems is ds. Okay, so I've just tried to remind you what s was. S was the arc length, and it was this integral. Well, I want ds. So ds is sort of the derivative of this. You know, if I took the derivative of this, ds, then I'm taking the derivative of this integral. And so I'm going to just knock out the integral, and I'm going to say that ds, the derivative ds, is this, without the integral symbol. And then, let me remind you what this is. So first of all, it's not r, it's r prime. You know, r was a vector-valued function. I already reminded you of that. But r was a an x of t and a y of t in general. So what's r prime? R prime would be an x prime and a y prime. And then what would be its magnitude? Oh, the magnitude would be the square root of x prime of t squared plus y prime of t squared dt. So this is ds. This is ds. And when you calculate ds, you replace this ds with what it is, and notice with what it is, it ends up with a dt. So you end up working this integral all in t's. I know it's presented like this, but the work involved to actually do it is turn everything into t's. Turn the function of x's and y's into t's based on the curve over which we're integrating. and turn the ds into t's based on the curve over which we're integrating, or based on this formula. Cool, here we go, let's do it. I need ds for my problem. Let's go, I'll go right here. For my problem, I need the square root of, this is my ds, it's the square root of, oh, I need x prime and y prime. I can talk like this. I need x prime and y prime. Or I can talk like this. I need r prime, which is x prime and y prime. Okay, there's two ways to talk. I don't want to confuse you. I can use this notation. I can kind of use this notation. I don't want to confuse you. They're very similar. So I need r prime, which contains x prime and y prime, which is, let's see, the derivative of cosine is negative sine, and the derivative of sine is cosine. So there's my x prime and y prime. I'm going to plug those right into my formula here. I need x prime squared, that's negative 2 sine t squared, and that's 2 cos t squared dt. All right, cool, that goes here. This big mess goes here. Now the truth is, this whole thing looks rather messy, but it's not. With all these squareds going on, there's a lot of cos squareds plus sine squareds going on here. Cos squared plus sine squared is 1. I got to filter through the 2's or the 4's or the square roots, but there's a lot of nice action going on here. Let's work on it. I'm going to get rid of these notes and move back over here. I'm working on this integral. It's going to be an integral from 0 to pi. You know, when I start working on this, it's 4 cos squared plus 4 sine squared. If you factor out, I'll write that down for you. 4 cos squared t plus 4 sine squared t. Out here on the end goes the ds. Let's work on this ds here a minute. It is the square root of, hey, that's 4 sine squared t and 4 cos squared t. Now the game is, factor out the 4, you're left with sine squared plus cosine squared, which is a 1, a multiplied 1 times 4. It's in a square root. The square root of 4 is 2. This ds is 2 dt. So that was pretty nice. At the end of this problem, the ds is 2 dt. And this, dude, this is just a 4, right? Again, sort of factor the 4 out. Cosine squared plus sine squared is a 1. This is a 4. This is a 2. This is an 8. This integral has turned into this. And the answer is 8t, when you integrate. Evaluated from 0 to pi, the answer is 8 pi. We just worked on a particular type of line integral. And that was a pretty good example. That was one quick example of a line integral. I explained everything kind of as I went. I didn't really explain it before I did it. I needed a function in 3D. That's z equals a function in 3D. I'm integrating that function over this curve with respect to the length of the curve. So, and here was a picture of the curve. And so our problem started with us trying to parameterize the curve, to put it in terms of t. You know, notice this thing is a single integral, and if it's a single integral, it needs to be done in a single variable. It's not a double integral where you have x's and y's. So we did have x's and y's, but it needed to be translated into a single variable. That's why we needed the x's and y's parameterized in terms of the single parameter t. And then we needed the s turned into t's, the ds turned into t's and dt's. So it's a process. That was a good problem. We're in 15.2. You got to start working on these. Now listen, what the hell is the meaning of this? That's a little tough. Let's see. The book talks about a few different interpretations. One interpretation is if this function happens to be a density function. Hello, Alec. If this happens to be a density function, then we're integrating this density function. Hang on. We're integrating this curve. Oh, okay, yeah. The book says, what if this curve is a piece of wire? And the piece of wire has various densities. The density of the wire depends on x and y. So here's a wire with varying density, and if I integrate that density along the curve of the wire, I think I just found the mass of the wire. Anyway, that's one contrived application of this line integral. Here's another one, a more geometric version of this is a 3D function, and by the way, the one I made up here is a paraboloid. I can draw this 3D function. It's a paraboloid like this. And I'm integrating it over a curve in the xy plane. The curve in the xy plane is this semicircle of radius 2. Let me make it a little smaller. Semicircle of radius 2. So what is going on? You could think of this as what? I'm integrating that function, which is like a height, all along that curve. You know, in the previous chapter, we were integrating a height over a region. A region, which was the height times the area of the region was a volume. This is not that. I'm not integrating over a region. I'm integrating along the curve itself. Nothing, no shaded area here. No. So I'm integrating. If this goes up and hits this, it's like the height of this. You could interpret this as lateral surface area. Holy shit, what do I mean? I mean, if there was a wall built here, a wall with this height along this curve, I think it would be, actually it would just be, I think it would just be something like this. And we just found the lateral surface area of that wall. That wasn't too hard. Actually, I don't think I have a varying height. I think when I'm on a circle of radius 2, I think I'm at a certain height around this paraboloid. I don't think I have a varying height here at all. That's why it came out pretty darn nice. 8, integrating 8 times t, 8 pi. We could work on more of those, but let's move on. Work on more of those. Let me see. Let me see if there's one in the book I want to do here. Yeah, this can get tough, and you can see why here. Watch this. Let's do another one. I think I'm going to go do another one here. In 15.2, I'm going to grab problem number 18 here. It's a tough one. What they want me to do is integrate along a curve. The function they want me to integrate is this. And of course, they're asking me to integrate with respect to s. So it's one of these again. It's one of these line integrals. They want me to do this line integral, and for 18, they describe the curve as this. They say I'm going counterclockwise around the square with vertices at, and then they give me these points, 0, 0, 2, 0, 2, 2, 0, 0, 2, 0, 2, 2, and 0, 2. Okay, I know what that is. Let's draw. I need a picture of this. So what I don't really need a picture of is the 3D shape. I am integrating some 3D shape over some curve in the XY plane. Not that one this time, a different one. But I'm integrating this 3D shape over some curve in the XY plane. The curve is actually a square that goes from 0, 0 to 2, 0 to 2, 2 to 0, 2 and back. Counterclockwise, they said. Counterclockwise. So here's my curve. I'm integrating along this curve. Wow. So one of the things I glossed over is when you do these line integrals over a curve, the curve should be smooth. And smooth, there's a technical mathematical definition for smooth. Both derivatives need to be defined, and that usually keeps the curve smooth. If the derivative ever becomes undefined, that may be a not smooth place. The derivatives, dy dt, dx dt, must be defined for the curve to be smooth. You know, forget the mathematical definition for a minute. It can't have any of these sharp points. So this is a not smooth curve. And so I can't do this all in one problem. You know what I got to do? I got to do 4 little problems. I got to do C1, C2, C3, and C4. I got to do 4 separate problems. I got to turn this, I got to do this problem, and I got to do C1, I got to do it for C2, I got to do it for C3, I got to do it for C4, and I got to add them all up. I mean, it's a pain, but we got to do it. What's nice is the parameterization for these curves is pretty easy. Let's talk about this C1 here. C1 is just this little curve. And by the way, it ain't much of a curve. It's a line from here to here. I think, let's see here, I got to parameterize this. I think x is moving. I think I want to call x t. I want to call x equal to t. I think y is stuck. Y is stuck at where it's at here, which is y equals 0. So I think y is stuck on 0 while x moves. Y is 0 and x is t. And I think t is going to go from 0 to 2. You know, it's kind of easy to figure out the bounds for t if t is x, which it often is, but not always. But if t is x, then look at this picture. On the x-axis, you're going from 0 to 2. So x goes from 0 to 2. If t is x, then t goes from 0 to 2. I'll tell you what, I got a lot of work to do. I got to do C2, C3, C4. I got a lot of work to do here. Let's do one and finish it here. Let's just finish one of these. So let's just take C1 all the way to the end here. Hey.
How you doing?
Oh, good.
Plan operations, we were just looking at your walls.
Yeah, sure.